Good evening. Comets are colourful fuzzballs in space that have a small rocky nucleus, a shimmering halo of dust known as a coma, and a long dusty tail stretching thousands of miles in length. They have been seen by skywatchers for centuries and were once believed to be omens of bad fortune. Over the last decade, a number of spacecraft have visited comets and have helped to reveal their secrets. In this month's programme, we look at some of their findings to help better understand the discoveries that await us from Rosetta over the next year. After a 10-year journey, the European Space Agency spacecraft Rosetta has arrived at Comet 67P Churyumov-Gerasimenko. The probe successfully entered into orbit around its nucleus on the 6th of August 2014, and the historic event made headlines worldwide. Lying at a distance of 251 million miles from the Earth, it takes a radio command 80 minutes to reach us from Rosetta, which lies just inside the orbit of a giant planet Jupiter. The comet is expected to reach perihelion on the 13th of August 2015, when it will be over 115 million miles from the Sun. Rosetta scientists have now begun the task of making observations of Comet 67P. The first temperature measurements of Comet 67P Churyumov-Gerasimenko were made between the 13th of July to the 21st of July, when Rosetta closed in from 8,700 miles to the comet to just over 3,100 miles. The observations were made by the spacecraft's visible infrared and thermal imaging spectrometer, VIRTIS, and revealed an average surface temperature of minus 70 degrees centigrade. This implies the surface is predominantly covered in dust rather than ice. Although minus 70 degrees centigrade may seem rather cold, it is 20 to 30 degrees warmer than predicted for a comet at that distance covered exclusively in ice. OSIRIS images show that the coma of Comet 67P covers an area of 93 by 93 square miles, about 150 by 150 square kilometers. The comet is actually a two-rock system which came together to form the peanut-shaped nucleus we see in the new images. It measures 2.2 by 2.5 miles in size, yet careful analysis of the first close-up images of the comet, taken on the 29th of July, show a jet of material originating from a crack in the surface of the nucleus where the two objects come together. The mass of the comet has been calculated to be 10 billion tons by monitoring the gravitational tug of a 2.5 mile wide nucleus exerts on the probe. 10 billion tons sounds a lot, but it means Comet 67P Churyumov-Gerasimenko has quite a low bulk density, something in the region of 300 kilograms per cubic meter. If you could put the object in an ocean, it would float. The calculation would seem to confirm suspicions that the comet is highly porous and may even hide voids inside its body. Scientists at the European Space Agency are now busy trying to find a safe landing place for the small Rosetta probe, Philae. On the 11th of November, Rosetta will try to place the Philae lander on the comet. It must attach to its nucleus, which is travelling through space at 12.5 miles per second. Knowing the location of these jets is of great importance to ensure that the Philae probe does not come to any harm. The science study of Comet 67P by the Rosetta spacecraft will need to be supplemented by ground-based observations of Comet Churyumov-Gerasimenko by keen amateur astrophotographers located mainly in the southern hemisphere. With a magnitude of plus 18.7, it is not an easy object to find. The comet is now located near the double star named Stella Zeta Sagittarii, moving between Messiers 54 and M70. When 67P reaches opposition, its closest point to the Sun, on the 13th of August 2015, the comet will have moved into Gemini the Twins. It can then be found a little above and to the east of Epsilon Geminorum, Mambusta, to give it its proper name. We believe its magnitude will then be 13.2, so that comet 67P will be visible in 8-inch telescopes. Ground-based observations are being coordinated by Colin Snodgrass and Padma Yanamandra Fisher. Padma is a senior research scientist at the Space Science Institute, Boulder, Colorado, in the United States. Together, they have set up a special face group named PACA Rosetta 67P, which stands for Pro-AM Collaborative Astronomy. Padma informed me that group members interact by sharing information, methods and techniques. Of course, compared to the fantastic detail observed by Rosetta and hopefully Philae, the ground-based amateur observations are a challenge, she said. Amateur observations provide a complementary global perspective of the comet, coma and activity, plus another set of data to compare against the legacy data from previous appearances. With multiple observing windows from both the northern and southern hemispheres. The group are keen for amateur astronomers from South Africa to get in contact and be involved with observing comet 67P. Tony Angel is an observer at the Searchlight Observatory Network at the Observatory Sierra Contravisa. He informs me that telescopes used by the group's amateurs range in size from small to 72 inches, and then there are the professionals with access to larger ones. When 67P gets bright enough for spectroscopy, then there are skills in the group for that as well, he said. Members of the group include astronomers Rolando Lungustri, who observed 67P during its last appearance, and Alan Hale. So if you would like to be involved in observing and imaging comet Churyumov-Gerasimenko, do look up the group on Facebook. So what are comets and where do they come from? Our solar system is made up of a sun in the centre and 8 planets. Nearest to the sun are the rocky planets Mercury, Venus, Earth and Mars, followed by a wide gap filled with over 3,000 chunks of rock known as the asteroid belt. Further away we come to the gas giants of Jupiter, Saturn, Uranus and Neptune. Pluto is a dwarf planet lying in the region astronomers call the Kuiper Belt, around 3,600 million miles from the Sun. Astronomers use the Earth's sun distance of 93.5 million miles as a unit of measurement they call the astronomical unit. On this scale, the most distant planet, Neptune, lies 30 astronomical units from the Sun, which is about 2.8 billion miles. Comets are members of the solar system, but astronomers believed are the leftover remnants from the formation of the planets 4.5 billion years ago. The best known of these is Halley's Comet, which orbits the Sun in a narrow elliptical path once every 76 years. It last came to perihelion on the 9th of February 1986. Comets are dirty big snowballs of rock and dust and come into two classes. Long period comets have orbits measuring thousands or millions of years, and many may never return to the inner solar system once past the perihelion, their closest point to the Sun. They originate in the farthest region of our area of space, known as the Oort cloud. For example, Comet C2013 Siding Springs, which has a period of 7 million years. On October the 19th, 2014, the comet will pass to within 26,000 miles of the planet Mars, 6 days before perihelion. It will then be of magnitude plus 7.7, lying in the constellation of Pavo, and visible in the southern hemisphere. From the surface of Mars, it will be a spectacular sight in the Martian skies, shining at magnitude -9. So please make a note in your diary. This distant region is named after the Dutch astronomer Jan Oort, and is a spherical cloud of comets believed to surround the Sun, occupying a vast space from somewhere between 2,000 to 5,000 astronomical units to as far as 50,000 astronomical units. That's over 4.6 trillion miles from the Sun. If you recall that Neptune lies 30 astronomical units from the Sun, you can see just how distant the Oort cloud is. Some estimates place the outer edge at between 1.5 and 3 light years. 1 light year measures 6 million miles, so again you have an idea of the vast distances involved. The region can be subdivided into a spherical outer Oort cloud and a donut-shaped inner Oort cloud. All of the 7 comets visited by spacecraft over the last 10 years come within the class of short period comets. They are named Halley, Giacobini-Zinner, Grigg Scalarup, Borelli, Tempel 1, Hartley, and now Comet Churyumov-Gerasimenko. Short period comets originate from the area of the solar system astronomers call the Kuiper belt. This is a region extending from the orbit of Neptune, the 8th planet, to approximately 50 astronomical units from the Sun, and is very similar to the asteroid belt, but it is far larger, 20 times as wide and 20 to 200 times as massive. The Kuiper belt is home to the dwarf planet Pluto. Some of the solar system's moons, such as Neptune's Triton and Saturn's moon Phoebe, are also believed to have originated in the area. In order to better understand the origins of our solar system and possibly life on Earth, planetary scientists are keen to carry out observations of these comets close up. The latest spacecraft from the European Space Agency, Rosetta, will do just that as it follows Comet Churyumov-Gerasimenko along its 6.4-year orbit around the Sun. Astronomer Fred Whipple was born on November the 5th, 1906, in Ohio. In 1945, he became a Harvard professor of astronomy, specializing in the study of comets. In 1950, he put forward a theory that comets are composed of ice and dust, which has become known as the dirty snowball model. In his paper, printed in the Astrophysical Journal, he said, "The nucleus is visualized as ices and other possible materials, unstable at room temperature, gathered together into a compact mass and combined with meteoric materials, all at extremely low temperatures of about -50 degrees centigrade. Vaporization of the ices by externally applied solar radiation leaves an outer crust of non-stable insulating meteoric material on the comet's nucleus." He added that heat transfer through thin meteoric layers in a vacuum was mainly by heat from the sun, and that the heat transfer is inversely proportional to the effective number of layers. Fred Whipple concluded that an appreciable time lag in heat transfer could occur for a rotating cometary nucleus. The momentum transfer from the velocity of the emitted gas would propel the nucleus, reduce the mean motion, and increase the eccentricity of the comet's orbit, he said. As it turns out, this is an accurate description of a comet. The first successful comet probe to test the data snowball theory was Giotto of the European Space Agency. It was launched towards Comet Halley on the 2nd of July 1985 and was a flyby mission. The spacecraft was originally a research satellite built by British Aerospace and modified with the addition of a dust shield as proposed by Fred Whipple himself, which comprised of a thin aluminum sheet separated by a gap and a thicker Kevlar sheet. Giotto was named after the earlier Italian Renaissance painter Giotto di Bondine. It was equipped with a camera known as HMC, or Halley Multicolour Camera, to view the nucleus, instruments to investigate the composition of Halley's comet, and detectors counting the impact of comet fragments on the craft's protective shield. On the 13th of March 1986, the mission succeeded in approaching Halley's comet at a distance of 370 miles, and there were some surprises. First, the nucleus was much warmer than had been predicted. In shape, it was likened variously to a baked bean or an avocado pear, and it was about 9 miles long and 5 miles wide, which is about 4 times the size of Comet 67P. The low density indicated that the comet was made up of fluffy material with water ice as the main constituent, together with other substances such as carbon dioxide, formaldehyde, nitrogen and ammonia. There was considerable surface structure, including a bright region which seems to have been a hill almost a mile high. There were craters and jets and 3 main areas of activity, yet all the jets seems to have issued from one small area on the sunlit side of the nucleus, and the remaining 85% of the surface was inactive. The rotation period was given as 7.3 hours, and there was a precessional period of 53 hours, so that the nucleus was behaving rather in the manner of a spinning gyroscope. It was also estimated that the comet would have lost about 300 million tons of material by the time that it moved back into the remote parts of the solar system. Only 10% of the surface was active, with at least 3 outgassing jets seen on the sunlit side. Analysis showed that Halley's comet formed 4.5 billion years ago from ices that had condensed into interstellar dust particles. It had remained practically unaltered since its formation. The measured volume of material ejected by Halley was 80% water, 10% carbon monoxide, and 2.5% mix of methane and ammonia. Other hydrocarbons, iron and sodium, were also detected in tiny amounts. However, the real shock was the colour of the nucleus. It was not ice bright, as many people had expected. It was black, reflecting no more than 2 to 4% of the sunlight falling on it. Astronomer Fred Whipple and Sir Patrick Moore were in the German Control Centre in Darmstadt as the science results came in, and Professor Whipple had been proven correct. Halley's Comet was indeed a dirty snowball. The plasma and ion mass spectrometer instruments showed Halley has a carbon-rich surface, so there must be a layer of carbon which protects the ice below from evaporating quickly and is an effective insulator. The nucleus surface was rough and of a porous quality, with the density of the whole nucleus as low as 0.3 grams per cubic centimetre. Compare that to 67p Churyumov-Gerasimenko, which is about 100 times less dense. The quantity of material ejected was found to be 3 tons per second for several jets, and these caused the comet to wobble over long periods, which was predicted by Professor Fred Whipple. The dust ejected was mostly the size of cigarette smoke particles. 2 kinds of dust were seen, one with carbon, hydrogen, nitrogen and oxygen, the other with calcium, iron, magnesium, silicon and sodium. The ratio of abundances of the comet's light elements were the same as that of the Sun's. The implication is that the constituents of Halley's Comet are among the most primitive in the solar system. Following its successful flyby of Comet Halley, Giotto went into sleep mode, ready for its extended mission. It was commanded to wake up on the 2nd of July 1990, when it flew by Earth in order to slingshot to its next cometary encounter. The probe then flew by the comet Greg Scalerup on the 10th of July 1992, which had approached to a distance of about 322 miles, 200 kilometers. Here again, the Giotto spacecraft successfully confirmed Fred Whipple's dirty snowball theory was correct. The flyby conditions were different from those during the Halley encounter, since Greg Scalerup would approach Giotto at an angle of 68 degrees instead of head-on. The bumper shield would therefore afford no protection. However, Giotto worked well and sent back some nice images of Comet Greg Scalerup close up. The 8 operational experiments, including the radio science investigation, provided a surprising wealth of data. Conditions inside the comet's ionized gas cloud were much different. The first cometary ions, charged particles, were detected 708,000 miles from the nucleus, about 12 hours before its closest approach. Scientists were surprised when an abrupt shock wave was detected on Giotto's outbound leg, but not clearly identified on the inward-bound journey. This is caused when the supersonic solar wind slammed into the plasma around the comet. The magnetic field strength was slightly higher than that of Halley's Comet. However, no activity was detected around the much smaller nucleus. Strangest of all was the discovery of unusual magnetic waves, each about 1,610 miles apart, near the comet. Activity arose and fell over a period of 70 seconds and increased in strength as time went by. The waves were generated by charged particles created from the breakup of water molecules around the comet as they moved in the magnetic field created by the solar wind. Following the cometary encounter, the science experiments on board Giotto were switched off for the last time on the 23rd of July 1992. The next comet to be visited by a spacecraft was Borrelli. NASA's Deep Space One flew past the comet's nucleus on September the 21st, 2001. It was steered towards the comet during the extended mission of the craft. The flyby of Comet Borrelli was also a great success and returned extremely detailed images of the comet's surface. The images were of higher resolution than the previous pictures of Halley's comet taken by Giotto. The plasma experiment by the Planetary Exploration Instrument reported that the comet's magnetic field was offset from the comet's nucleus. This is believed to be due to the emission of jets which were not distributed evenly across the surface. Despite having no debris shields, the spacecraft survived the comet passage intact. One question that planetary scientists wanted answers to was whether comets carried organic chemicals which may help kickstart life here on Earth. Two British astronomers, Fred Hoyle and Nalin Chandra Wickramasinghe, then entered the frame. Chandra Wickramasinghe, a former student of Sir Fred Hoyle, is a distinguished astronomer who made important contributions to the theory of cosmic dust. In 1974, he proposed a theory that dust in interstellar space and in comets was largely organic. In his later years, Fred Hoyle became a staunch critic of theories used to explain the origin of life on Earth. With Chandra Wickramasinghe, Fred Hoyle promoted the hypothesis that the first life on Earth began in space, spreading through the universe via what astronomers call panspermia, and that evolution on Earth is influenced by a steady arrival of viruses arriving via comets. Their belief that comets had a significant percentage of organic molecules was well ahead of its time, as the dominant views in the 1970s and 80s were that comets largely consisted of water ice, so the presence of organic matter was considered highly controversial. What was needed was a spacecraft to test the idea by visiting a comet, collect a sample of cometary dust, and return it to the Earth for analysis. The next mission was NASA's Deep Impact Space Probe, launched from Cape Canaveral on January 12, 2005. It was designed to study the interior composition of the comet 19P Tempel 1 by releasing an impactor into the nucleus. Initial results were surprising, as the material excavated by the impact contained more dust and less ice than had been expected. The material was finer than expected. Scientists compared it to talcum powder rather than sand. Other materials found while studying the impact included clays, carbonates, sodium and crystalline silicas that were found by studying the spectroscopy of the impact. Clays and carbonates usually require liquid water to form, and sodium is rare in space. Observations also revealed that the comet was about 75% empty space, and one astronomer compared the outer layers of the comet to the same makeup of a snowbank. Based on its interior chemistry of Comet Tempel 1, astronomers believe that the comet formed in the Neptune region of the solar system. A comet that forms further from the Sun is expected to have greater amounts of ices with low freezing temperatures, such as ethane, which was present in Tempel 1. Astronomers believe that other comets with compositions similar to Tempel 1 are likely to have formed in the Kuiper belt.
In 2006, NASA's Stardust mission flew through a comet's tail and brought a sample of dust back to Earth.
The dust was analyzed in laboratories here, and they found, of course, interesting minerals there, but the most interesting thing I think they found was glycine. Glycine is an amino acid which is used in the DNA of life on Earth. It's one of the 4 basic amino acids used in our DNA.
Ground-based observations of comets are extremely useful, but the biggest leap forward in cometary science has been from space missions.
NASA returned to Comet Tempel 1 in February 2011 when the Stardust New Exploration of Tempel 1 Next mission observed changes since Deep Impact's 2005 encounter. Here is a colour image showing the nucleus of Comet Tempel 1. The flyby of Comet Tempel 1 by Stardust Next on February 14, 2011 revealed new parts of the surface hidden from view of a Deep Impact spacecraft in July 2005. The new data allowed mapping of nearly 3/4 of the surface and show the shape of the object is similar to a rounded pyramid with a mean radius of 1.7 miles. The shape viewed from 6 directions and colour by the relative heights is shown in the top illustration. One of the striking features of this low-gravity object is that there are regions of different types of geology and that these occur at different relative heights. Areas that are relatively high are rough and have many pits, tens to hundreds of metres across. Low-lying regions have much smoother topography and even display deposits which have many characteristics of having been covered by flows along the surface, filling in below areas. These flow deposits are up to tens of metres thick and some are over 1.8 miles in length. The 3 main low regions and outlines of likely flows are shown in the lower part of the illustration. This second image, obtained by NASA's Stardust spacecraft, shows a side of the nucleus of Comet Tempel 1 that had never been seen before. In the image, 3 terraces of different elevations are visible, with dark bands, scarps or slopes separating them. The widest of the banded slopes is about 1 mile. The lowest terrace has 2 circular features that are about 500 feet in diameter. In this last image of Tempel 1, taken on February 14, 2011, water ice is seen in some of the craters. By analysing data and images taken before impact, Deep Impact scientists detected water ice in 3 small areas on the surface of a comet. This is the first time ice has been detected on the nucleus or solid body of a comet. Before Deep Impact, there existed few observations of nucleuses not obscured by the coma. Among previous cometary missions, the most notable of such observations was the Deep Space One mission to Comet Borrelly, which searched unsuccessfully for evidence of water ice and other volatiles on the comet's surface. This brings us back to Rosetta, which is now orbiting Comet 67P Churyumov-Gerasimenko. Rosetta's mass spectrometer, COSIMA, managed by the Max Planck Institute for Solar System Research in Germany, is now beginning to detect cometary dust. On Sunday the 10th of August, COSIMA exposed the first of 24 target holders aiming to collect single dust particles. The number is likely to be small now because of the comet's great distance from the Sun. However, as 67P travels closer to the Sun along its orbit, the comet's activity will increase and more dust will be within reach. For now, scientists are planning to keep the target exposed for 1 month, and they will check on a weekly basis to see if small dust grains have attached to the detector. The detector consists of a gold plate covered by a 30 micrometer thick layer of metal black, which has a very low reflecting ability. Tests in the laboratory have shown that this layer should decelerate and capture cometary dust particles impacting with velocities of 225 miles per hour, 5 times faster than a speeding car. If planetary scientists of the European Space Agency are lucky, Rosetta will also be able to detect genetic material such as glycine in the collected dust grains of Comet 67P, with confirmation coming from the Rosetta lander Philae. Therefore, there is much to look forward to over the next 12 months, and I am quite sure there will be many surprises along the way. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.